Hello everyone. Okay, today, to be honest, this is one of the episodes that will not get views. I know from the get-go, I will do all the work and this will not get views, and I'm okay with it. This is one of the episodes I actually do for the community. So the reason I'm doing this episode is in one of my previous videos, I mentioned the strawberry test. And I was saying the reason that AI models struggle with the strawberry test and counting how many R's in the word strawberry is because of the way it does the prediction. And one of the community members, who is mostly smarter than me when it comes to AI, corrected me and said, no, it's more about how it does the embedding and the tokenization at the early stages of the training of that model. So I said, this is a good opportunity for me to dig deeper into understanding artificial intelligence as someone learning and sharing my journey with everyone. And this brings me to this episode. So I did some homework, I looked at some references, I read through it. I'm going to do it all over again here. And this is the type of video, if you're going on a long run, long walk, drive, it's something that you listen to. I guarantee by the end of this video, this is my value proposition to you, that you will have definitely more knowledge of how AI models work than the average person. Now, it might not be perfect, but this will be giving you maybe keys and ideas and resources that could give you some inspiration to do more than I did with this knowledge. So you can research it more, understand it more, and hopefully share that feedback with me. So today we're going to start with some basics. I've already covered a video on the high level areas about artificial intelligence, the different type of networks, how they work, and even I shared some resources on demoing such artificial neural networks, how they work, so at least you can imagine what goes behind it beyond the theoretical. And today I'm going to do the same, but I'm going to focus on a different area. Today we're going to focus on two things: the transformer architecture, which is the thing that revolutionized everything we know today about artificial intelligence. It brought us ChatGPT, Claude, all of these kind of models that we love today. And then I'm gonna look at the future, what could be the next phase of evolution for artificial intelligence models. And finally, if you wait till the end, I'm gonna give you 3 or 4 tools that you can play with that can help you understand better everything that we go throughout the episode. And even you can share it with others and help you explain to them what is a transformer and visually explain it to them rather than doing an hour probably of sharing links and articles and reading through text. And by the way, you feel free to jump till the end and just go to these resources, see the demos. But I guarantee you will not capture the full value of this. Spend some time, maybe you can skip between chapters, but spend some time to go through the flow of the video and then go to these demos. It will be much more valuable for you. I will be repeating certain things. I'm not an expert, so I found myself when trying to learn things on YouTube that there's two types. Either I go watch an expert doing things oversimplistic, or I watch an expert actually complicating things that I don't grasp or understand. But I found a different type of video, not so mainstream. I'm going to do the same, which is someone trying to learning real time, the concept that they're talking about. And I found that more relatable and in many cases helped me grasp such concepts much better than getting it from the expert, so to speak. So let's explore this together. My name is Samer, if you don't know me. My channel is all about AI and tech and helping people who are not technical, like myself when I started my journey, learn it, use it in their personal life and their careers to improve it, make it better, take it to the next level. And with this, let's just get started.
Subscribe to Daddy's channel. The mic.
Okay, before I start, everything I show you here, it will be in the description. All the links and resources, these are things created by super smart, amazing people that are giving out this information to the world. I will link it in the description. I've created, as I mentioned before, a video with the AI basics, networks, how they work, the types of networks, at least the common ones. I'll also include it in one of the cards throughout the video, and I'll include it in the description so you can have everything in this video in one place for you to do your own research or expand on it if you want to do so. And with this, let us start with quickly, I will not spend lots of time, with the fundamentals, and then we can actually move to the important part, which is the transformer architecture and why it's special. And closer to the end, as I mentioned, we're gonna actually see why it gets the strawberry test wrong, and we're gonna demo that, see why and how we can fix that, maybe in the transformer architecture, but in general, why it gets it wrong for the most models. Okay, so here you see this visual, which I showed in the previous video, and I'm sure you've seen it before. The whole premise for someone who doesn't understand artificial intelligence yet, maybe this will help you to follow along with the video, is that someone somewhere decided to replicate the way we think, the way our brain functions into a program. Can we do it artificially? Can we do it through machines, basically? And what they've done, literally, they were influenced by the way how our brain cells operate and work and how the anatomy of those cells is. So you can see the cell, how it looks. I will not go over the scientific terms of the cell, but basically it has branches as inputs going into the nucleus, which is later on in AI, we call it a node. And then it has an output that goes probably to interact or connect to other nucleus cells in the brain. And you can multiply that by billions and billions of cells, and that's what gives us what we perceive as humans as intelligence or IQ. So this is how our brain works. Now, they came and they tried to replicate that through a program in mathematics. Now, this idea is not new. It's actually pretty old, but we never had the computing power, we never had the data available to actually start working with these things in real life. As technology progressed, we started doing it, implementing it, playing with it, and we got along the years certain breakthroughs. Obviously, the transformer was one of the most recent and probably the most significant one that we can recollect today. And it moved artificial intelligence from something that researchers used to work with to something for the open public to actually make use of in tools that we use today. Everyone probably is using artificial intelligence in one way or another. So you can see here, this is the node, which is basically the nucleus, and it gets a bunch of inputs similar to the branches that we see here. And again, this is all mathematics. So these are computer programs on top of machines, but in the core of it, all of this, as you will see today, it's all mathematical equations that make sense of data as it flows. And by the way, today as humans, we are not able to fathom all of these calculations at once. We know how it's built, we know how it's calibrated, and we judge based on the design of the model, the input, the output, if it's a good one or not. There's methods to do that. So we have all of these inputs, which are x1, x2 until xn, and then we have the weights. Now the weights is the end result. The easiest way to describe it is the value we care about, because this is the value that is assigned to a model after it's trained, and this is what gets a model to operate in the way we want it, and for us to use it later as a trained model. So this is the network for training that model and generating all of these weights that we will use later on in any model for operation, for use. Now, all of these inputs go to an activation function. And the easiest way to describe the activation function, it's a function that will decide if that node will activate or not. So when we think about something in our brains, not all our cells are working at the same time. It's parts of our brains address certain areas or certain questions or certain topics that or activities it's taken care of. So it's not every time we have a thought, the whole brain lights up. It's just parts of that brain. And the easiest way for me, at least in my mind, to understand activation function, it is exactly that. It is the function that tells this node, oh, based on that input, you're going to fire up and continue to another node, or you're not going to fire up, you're not going to activate, basically, and things will stop here. And there's a sum, which is a transfer activation function. Basically, it takes all these inputs. There's a function that runs over these inputs, and it is what puts things together to go for the output. So this is the first fundamental idea. And again, let me scroll down just to show you how these networks look. Again, this is a very simplistic look of networks. It is, again, similar to the brain, billions and billions of what they call parameters. So these parameters are the weights, but you can think of it when they train these neural networks, they actually train them through billions of nodes. And eventually we have those weights that we'll use later on. This is just a view for you just to imagine how it looks. So you'll have an input layer. Basically, this is where you push the training data or whatever data you need to train that model. And you have so many layers of hidden layers, what they call hidden layers. And then you have an output layer where you get the output. This is why they call it deep learning, because you have so many layers of hidden layers within that neural network that makes it really deep. So the data has to go a long way from the input layer until it reaches the output layer. And you can see at each stage, there's that sum and activation function shown in the equations in the bottom. So this is fundamentally what we are looking at when we talk about AI. And this idea, again, is old. Now, something changed along the way in terms of the architecture of these things that made it much better in reasoning of some sort, and but more importantly, in having certain aspects which simulate memory or context understanding. Because at the end of the day, if I give you a sentence, that sentence is highly linked in your brain to a context. So, for example, if I mention the cat went out to the field and it ate the mouse. So once I say it refers to the cat. This is the context that your brain will start linking it to the cat. Computers can't do that. And the evolution that we have in the technology actually helped us to give it the ability to understand that this word is actually linked to cat. And that happened through the concept of attention. What words in that sentence should the model, or your brain for that matter, give attention more or less? What are the more related or less related words in a sentence that are important for you to comprehend or important for the machine to comprehend? So this is our focus, the attention part, when it comes to artificial intelligence models. But at the back end of all of this, it's all artificial neural networks that in simple terms look like this. Now, let me move to another fundamental thing, which maybe not so related like other things I'm going to show you here, but I think it's important. So I talked about it in my first video. This is the convolutional neural network, and this is a type of networks, or CNNs. It has to do more with image or other areas, less text, but these are very similar in one way or another, but they definitely benefited as much as the conventional networks I just showed you from the transformer architecture in artificial intelligence. And the way those networks operate, so let me just take you down. Again, you can see always there's this kind of view of how the brain works, and then they show you how the network works. It works more with images, and you can see it's that unique area that it addresses. And it's basically a network that cuts down an image to, let's say, pixels or smaller parts. They call them convolutions. That's why it's called the convolutional neural network. And each part becomes basically a matrix of numbers. At the end of the day, when we look at an image, the colors in it, the lights, it's just a number. It's a numeric value that the computer translates into an image when it's shown to us. And when it handles that image as well, it's numbers behind it. So it takes that chunk of the image as a convolution, turns it to these numbers, and then does something called kernels into it. Basically does modifications. Those, by the way, could be as simple as increasing contrast or doing other things like highlights. It helps it break down that image to certain kind of aspects or basic or simple way of looking at that image, which might not be the same way we look at the image, but it eventually will help the AI network understand somehow what it is looking at. So it does all of these convolutions, again, multiple layers and the kernels, and at some point it flattens all of that out and pushes it into a normal neural network or feed-forward neural network. and then it gets an output. So let me show you in this, again, you can read this on your own pace. This is not the topic of the episode, but this is one way of looking at it. And by the way, in the episode that I will link, I give you a chance or a link or a tool where you can do this for yourself. You can build the network. You can actually see how it's predicting the input image versus the output. So for example, this is an image of the number 2. And you can see that this design is taking this image, breaking it through convolutions, and you can see here convolution 1, convolution 2, and does all of these needed kernels. And you can see it's multi-layered at each of them, and then it's flattened here, and then it goes through that feed-forward network, and eventually you get an output. The output here is 0, 1, 2. Each of them will be assigned a probability, and if the network is done right, the probability for 2 will be the highest, and then it will tell you, I predict that what's written in that image is the number 2. So again, I know this is just something for you to keep in mind, that this definitely benefited a lot, this type of network, from what we have when it comes to the transformer architecture. Again, just one more resource for you, because this might come up and be mentioned as convolutional neural networks later on while we are reading into the more detailed aspects of the transformer architecture. Now, let's spend a little while here on the activation function, because those are very important when really understanding how neural networks or artificial neural networks work. Again, I am trying to learn as I go with you. So if you find me struggling, it's part of me thinking out loud with you, and for us both to get to a place where we better understand all of this. And this will be the theme of the whole episode. So I hope you enjoy it. Okay, let's move on. So what does an artificial neuron do? Simply put, it calculates a weighted sum of its inputs, adds a bias, and then decides whether it should be fired or not. So basically what I already explained. So this is Y is the output, and then you have the sum of weight multiplied by the input. So this is the W multiplied by the X, adding to it the bias. And again, the bias is covered in the first video. It helps out in really fine-tuning that model as you train it, into reducing the losses and basically the errors as it's being trained to the data it's fed. Again, it's a different area of its own. We're not going to focus on it today, but just understand that this is the equation behind the activation function. Now, the value of Y can be anything ranging from minus infinity to infinity, and then neuron really doesn't know the bounds of the value. So how do we decide whether the neuron should fire or not? Why this firing pattern? Because we learned it from biology. That's the way brain works. The brain is is a working testimony of an awesome and intelligent system. So again, it's all the same theme. It's the way our brain works, and we're trying to replicate it into technology. We decided to add an activation function for this purpose, to check the Y value produced by a neuron and decide whether outside connections should consider this neuron as fired or not, or rather, let's say, activated or not. So the same thing I just covered before. Again, the activation functions are simple functions, and there are so many types for different uses, or sometimes the combinations of those types within the same network. But here, let's just go over it high level. I will not go over each type of function and what it does. It will just give you the idea of how that function works. It gets something and it gets something out in a certain way. And that could tell the network, yeah, this is activated or not activated. And the first thing that comes to our mind is, how about a threshold-based activation function? If the value of Y is above a certain value, declare it activated. If it is less than a threshold, then say it's not. So great, okay, this could work. Activation function A, activated if Y is larger than threshold, else not. Alternatively, A equals 1 if Y is higher than the threshold, 0 otherwise. So, okay, so this is called a step function. So this is one type of activation function. So you can see whatever inputs come, if it's less than 0, the out will be 0. If it's more than 0, the output will be a flat 1. So here, if the Y is negative, the output will be 0. And basically you can tell 0 means it's not fired. There's nothing that could happen with a 0 of some sort. But if the Y is positive, then the output is 1. So that activation of that node carries on and considered as activated or fired. So let's just quickly look at if there's something more interesting here. But I think you get the idea of the activation function. Now, it goes here into the types of activation functions. So here we have a linear function. So these are important, and nonlinear function. So the sigmoid function is one of the most important, and it's a nonlinear one. So you can see here again, it's the same concept. So if we have something negative, again, you have to see where it falls into the chart here, and then you can see what the output will be, right? And the same goes if it's positive. So this just gives a value on the curve based on the x's coming in, the x's and the y's basically, and the sum of them coming in, and it will give a y which will be somewhere on this curve depending on the sum that it is getting. So at the highest range of it, if the sum is equal to 6 or more, the output will be 1. If the sum is smaller of -6, it will be 0. So again, this is one way of one equation of deciding what nodes fire and what's not. And again, all of these things beyond my expertise, but it is the way I think about it. All of these things are levers for the people designing a model to put it within their network to get certain performance out of that artificial intelligence network that they're building or the model that they're building and training. Again, here you can look at the link at your own pace. There's so many types of activation functions. This is a linear one. So anything negative will be 0. Anything positive will work against that linear line here. So if it gets, let's say, a 5, it will be probably visually, I'm looking at a 5. So this is one-to-one kind of linear function. So it's just anything positive will be the same value as the sum of the input. Anything negative is 0. So it just removes the negatives, this activation function. So there's so many types, so many things that you can look at, but you get the idea. The activation function fundamentally is a function that we design to decide which neurons continue, carry on, or fire basically, or activate, and which ones do not. Now, let's jump to one more concept. This is called the backpropagation algorithm. And this is the way where actually models started getting trained. And it is an algorithm that gave the models the ability to see what's happening going forward when the data is progressing into the network and the errors that are taking place, see that errors in previous steps in simple terms, and try to correct them somehow or modify the way it's running so it will reduce those errors. So we'll just go through it. Again, it's a concept that helps a lot for you to understand later on as we progress through the session towards what we need to aim for, which is transformer architecture. So let's just go quickly through the main parts of it. So backpropagation algorithm is probably the most fundamental building block in a neural network. It was first introduced in the 1960s and almost 30 years later in 1989 popularized by Rummel, Hart, Hinton, and Williams in a paper called Learning Representations by Backpropagation Errors. So again, I might have butchered their names. I apologize for that. But again, it's the algorithm that helps us manage those errors and get the model to actually learn and train as it goes. The algorithm is used to effectively train a neural network through a method called chain rule. In simple terms, after each forward pass through a network, backpropagation performs a backward pass while adjusting the model's parameters, weight, and bias. So we've seen the weight and bias. So the bias, if I didn't stress on it, actually it goes into the node, by the way. So these are some levers to tweak that model and how it will later on perform. So what this does, it allows not only feed forward kind of path for the information through the network, but also a backward path, which will allow that model again to modify weight and bias to perform better supposedly in the future. At least this is the concept behind it, and this is happening or being used in neural networks since that time on. Obviously, this have evolved a lot Definitely it has evolved a lot in the way it is being implemented or not. Okay, so I'm learning as I go with you, but it is definitely something as I learn or read into artificial intelligence, like it's one of the concepts that you need to grasp to a certain degree to really understand how the technology works. So again, here is just a look at the network. So you have the inputs. Again, these are going through the hidden layers that we talked about before, and you can see the nodes here, and eventually it goes to an output. And the input, so this is just describing what we are looking at. So you have an input layer, and again, this is the compilation of the inputs and weights, basically the summation, I guess. You have the hidden layers, again, with their own equations. Again, this, I'll give you a tool to do all of these calculations if you want to do so yourself. This is, I think, the barrier of how deep you want to go in your understanding of the models. My interest is to have good understanding of the concept and how that works. Maybe touch the surface of the equations. I'm an engineer, I enjoy these things, but this will be time consuming. If it's your thing, I will give you what will help you really tweak these things, look at them as they work step by step later on at the end of the video. But just understand that each layer, each function, each step has some numbers and modifications or manipulations to those numbers, is maybe the best term to use here. And okay, so here activation A2, okay, and E3 are computed. So here is just talking about the type of activation function it is using. So it's giving 3 examples. We talked about the sigmoid, there's the ReLU and the tanh. Each of them, as we've seen, does a certain function to manipulate the output based on the sum of the input and weights to activate or not activate a node. Let's go just to the important part of backpropagation. So this is going through all of the details of the equations. What I'm interested in, the backpropagation and computing gradients. So according to the paper from 1989, backpropagation repeatedly adjusts the weights of the connections in the network so as to minimize a measure of the difference between the actual output vector of the net and the desired output vector. So those talk, by the way, there's 2 types of data that they usually use in these things: training data and validation data. So training data is the data that you actually push through the network to train it. Validation data is the data you use to test the output of that network and if it matches the training. So basically backpropagation, maybe in a simplistic term, it does one run, checks the output, compares it to a validation data, sees the difference. And by the way, it does it compared to the training and validation data. So you have what is called training loss and validation loss. Basically 2 types of errors. And it looks at those errors and how wide they are, or how big the error is, or how small it is. It will again be fed back to the network to modify or tweak the weights and biases. So it will try again and try to reduce the error for the next run and so forth until a stage where it's satisfactory. It is set as satisfactory, where it holds and stops the training for the model. In other words, backpropagation aims to minimize the cost function by adjusting network's weights and biases. So the cost function is mentioned in this article. You can read about it. The level of adjustment is determined by the gradient of the cost function with respect to those parameters. One question may arise: why computing gradients? So again, it is part of the math of doing backpropagation and managing these artificial neural networks. I will not go through it today. You will have the link for this article for you to dig as deep as you want. Now, this is just a visual I wanted to show before we move on. It basically looks like this. So you can have the forward feed type of movement within the network, but also you have the red arrows, which is the back propagation. So you can see that goes back, feeding to these nodes, and then the nodes will modify or tweak the weights and biases, and again go back to feed forward and see what output that actually generates within that neural network. Okay, so let's move to the next part here. Okay, so now we are getting into the interesting stuff. Ahead of the transformer architecture, the most prevalent type of networks that were used are the recurrent neural networks and long short-term memory networks, LSTM. So I think it's very important for us to understand what was basically the height of the technology before the transformer architecture, and what was the issues within that architecture or that technology at that time. And later on, we will find out what actually the transformer architecture solved compared to what we had. And again, by the way, the transformer architecture did not replace fully these type of networks. These are networks that are still powerful tools that are just enabled to much better perform in terms of quality of output compared to just working alone through these technologies. So still, recurrent neural networks are a very important part of the technology of artificial intelligence and how it's designed, trained, and delivered to the consumers or the users of that technology. But at that stage, the main thing was for developing artificial intelligence concepts was the RNNs, which is the recurrent neural networks, and the long short-term memory network, which is LSTM. And those are variants, sort of speak, of the same type of network. So we'll go through that just to see what was there ahead of transformers, and later on we'll start getting to the important stuff when it comes to the version of artificial intelligence in concept, basic concept, that we are enjoying today in everyday life. So let's go through the introduction. In recent years, recurrent neural networks and their specialized variant, so it's a variant of the RNN, long short-term memory LSTM network, have emerged as powerful tools in the realm of sequential data processing. And here I would focus on the word sequential. So this is one of the areas or the limiters in this technology at that stage, that things went into sequence. Tokens or data went into sequence, and the context was not there because it's going into sequence. From natural language processing to time series forecasting, these neural architectures have shown remarkable capabilities in capturing temporal dependencies and patterns. So the basics of RNNs: imagine a traditional neural network. It receives inputs, processes them through hidden layers, and generates an output. However, so this is what we already covered, the normal neural network. However, RNNs add a crucial twist: memory. They incorporate their previous output back into the network, allowing them to remember past information and influence their current processing. So this is not ideally backpropagation, but it sounds just like it. It just retains for some time the information, or for a longer period, the information within the network. So that could be for backpropagation for error. This could be for context, but it's again limited. So the output of one node goes back to the previous node, so it can somehow return that kind of loop, which runs for some time, I think. And we'll get the details a little bit as we go through this article. The architecture of RNNs. RNNs are a type of neural network that has hidden states and allows past outputs to be used as inputs. So past outputs are used as inputs. So I'm just imagining with you. So it runs and it takes the output at each layer as an input again for the same layer. Maybe we'll look at it now. And this will get the network as it's being trained to know what happened last time, basically. What happened the last time the data went through that network? Okay, this was the outputs. Now it might modify differently, either for certain quality parameters or to reduce the errors that we talked into the backpropagation. I think this is different in that sense from backpropagation. So backpropagation just takes those errors back through the backward feed and provides them for tweaking the weight and the bias. This one just literally is recurrent. So it takes the output, feeds it back as an input. So we have the inputs, which is the X, if you remember, Xi or X0, X1 until Xn. And then we have the weights. And this network will have one more input, which is the output that the same node generated previously. So the next time it runs, it has the previous output as one more input to consider. Okay, so this is just a high-level architecture. So let's just read quickly the basic building blocks. So the basic building block of RNN is a recurrent unit. This unit takes two inputs, the current input X, which is here. So this is the current input, and the hidden state from the previous time step. The hidden state A acts as the memory, carrying information about what the network has seen so far. Okay, so it's not as simple as the same output of the node. So actually, it's the output from the previous state of what the network has seen so far. We'll hopefully maybe we can see more details around that later. But basically here, if you're looking, this is the A. So this is the memory part of it. And this is the output. So we have inputs, we have outputs. This is one hidden layer, I assume. And this hidden layer is getting the previous state of what the network has seen so far when it comes to the perspective of this layer. So I assume this layer has much previous layers and layers to follow it. So it only sees what went through the last time or the last state of previous layers. Okay, let's carry on. So example of RNN machine translation. Okay, sentence, I'm going to eat lunch. An RNN translating this sentence to French might initially translate eat to, okay, I will not even try to pronounce French. I'm going to definitely butcher it. But okay, this is the French word of eat, I assume. However, or one variant of eat in French. However, if the preceding sentence in the conversation was, would you like to join me for dinner? The RNN should understand that eat refers to lunch in this context and translate it to something else in French instead. This shows how RNNs can use context of surrounding sentences to improve the accuracy of translation. So they have context, but again, I think it's limited context. But this is the value that RNNs brought to the technology. It gave the network some memory and some context based on the data fed into that network. So let's go through quickly the different types of RNNs. One-to-one RNN processes single input and generates a single output, useful for tasks like predicting the next word in a sequence. One-to-many RNN processes a single input and generates multiple outputs used in music generation, where one melody becomes a sequence of notes. Many-to-one RNNs processes multiple inputs. I think this is the typical one we understand, and generates a single output, common to sentiment analysis, where multiple reviews lead to a single positive or negative sentiment. Many to many. Okay, so this is just types of the network that you can build. Challenges with, okay, this is where the money is. This is what we need to, I think, understand before we start moving to what happened later on in the evolution of this technology. While RNNs are effective in capturing short-term dependencies in sequential data, they often struggle to learn long-term dependencies. This is due to the vanishing gradient problem, where gradients diminish exponentially as they are backpropagated through time, leading to difficulties in training the network to remember distant information. Okay, so the vanishing gradient problem, the easiest way I'll describe it, I don't know if it will be explained later on, I forgot honestly. Remember, you're dealing with numbers and fractions of numbers. So in the recurrent neural network, backpropagation, I assume from reading this, happens if these gradients, or basically the values that are moving layer to layer in the network, are reducing. At some point, these gradients will vanish. It will go down to zero. So it will lose the information that it had. So that will limit its ability to maintain that context for a long time. And I think the opposite could happen. So the opposite of the vanishing gradient problem. So it can actually grow until a high value, or maybe one, limited at one. I'm not sure. But the problem of how you handle those numbers within the network as you train it is a challenge. One of them here is the vanishing, or the main one here is the vanishing gradient problem. Again, as it moves through the nodes, if these values of the gradients are just reducing, and all of this is happening through, in many cases, multiplications and sum. So if you keep multiplying by a smaller number, obviously that number will keep on diminishing, and it will go to a too small value, maybe close to this zero, where the state of the training or the model that you have vanishes. It goes away. I think this is what is meant here. So let's look at the back propagation through time. So this is the network. Okay, so we have here inputs. These are the nodes. These are the outputs, and we'll see what L is. But again, so we get this is the feed forward. This is the back propagation. And as it goes back, this is where the gradient could go down to 0. Okay, so somehow here it operates as the network that we know, but it just has the element of the recurrent fact, which is, as I said in the which I suspected in the beginning, it is actually the same or some kind of modified back propagation algorithm that makes it recurrent as a network. So yeah, okay, so it's good. They're talking about vanishing gradient. When backpropagating errors through many time steps in an RNN, gradients tend to diminish exponentially as they propagate backwards through time. This phenomena can occur due to the repeated multiplication of gradient values during backpropagation, leading to a very small gradient. Consequently, early time steps receive negligible updates during training, hindering long-term dependencies learning. So I think it is the same idea I had, because when it goes in the backpropagation path or the backward path or the backward feed path, it's being multiplied by smaller and smaller gradients, and that leads to the values to diminish down to 0, more or less. So it will lose its state as a model. Okay, so standard RNN gradient flow, vanishing gradients. So this is just a depiction of what happens. So vanishing gradients, many values are less than 1. So you have the activation function, weight initialization, network architecture. Okay, when the weights are very small, they get smaller quickly by multiplying in the backpropagation process, dropping down to 0, making the model unstable. That's why it's called vanishing, because the gradients vanish. Okay, exploding gradient. So this is the opposite of it, which I mentioned. Conversely, exploding gradient refers to the situation where gradients exponentially grow during backpropagation. This often happens when the network's parameters are initialized poorly or when the network architecture is not properly designed, causing gradients to increase uncontrollably. Exploding gradients can lead to numerical instability during training, causing the model to diverge. Okay, so again, this is the other scenario where many values are higher than 1, exploding gradients, gradient clipping to scale big gradients. Okay, again, it's all fundamentally means there's a big problem with recurring neural networks of loss of state. So it has a memory, which is good, was a big development, but they remained with the issue of not being able to keep that network stable for longer times. Now, they made a variant of that, which was called the long short-term memory network. So let's read about that and see also what's the issues with this one and what was able to solve and what it couldn't solve when it comes to this technology. To surmount the limitations of conventional RNNs, LSTM networks emerged as a breakthrough innovation. Armed with a sophisticated memory mechanism, long short-term memory networks excel in capturing long-term dependencies with finesse. So it's an RNN that could hold memory for long-term. Peering into the architecture of LSTM networks, okay? In addition to the inputs, recurrent and output layers, LSTM networks harbor memory cells designed to store information over extended periods. Governed by gate mechanisms, these memory cells regulate the retention, forgetting, and updating of information at each time step, circumventing the vanishing gradient problem and adeptly modeling long-range dependence. So basically, what's different is that they have a memory cell. We'll see what that actually is. That will solve the vanishing gradient issue, and it holds memory for a longer time. So let's look at the key concepts. Okay, maintain a cell state. So the state of that cell is maintained for in some way or another. Use gates to control the flow of information. Forget gates. Gets rid of irrelevant information, store gates relevant information from current input, selectively update cell state, output gate returns a filtered version of the cell state, backpropagation through time with partially uninterrupted gradient flow. Okay, so that's interesting. So it has some kind of gates, and I understand gates as rules, basically equations, functions. Some of them will get rid of irrelevant information, probably information out of the bound of certain limitations. It's able to store some of that in certain gates and then update the state of that cell and then return filtered version of the cell state. Okay, so again, you can see here, it's a complex cell. So this is the architecture within the node. So you have the input, you have the output, and this is what's happening between. All of these, let's call them subnodes. Okay, maybe this is the best way to describe it. It's certain functions that either retain, modify, eliminate certain values from the input going to the output. The best way I would put it, it's a more complex, more sophisticated activation function. At least this is how I understand it so far. So this is the architecture and there's a legend for it, so it will help us understand. So X is the input. So let's see the first, okay, the red bubbles here, those are the biases. Okay, that's good. The plus, this is element-wise summation and concentration. So this is a function that adds the, again, this is the, let's say the ideal activation. So adds all these inputs and I assume, okay, so this is the recurrent element into this network. So you have the output of the previous block coming here in the orange. So we have inputs, biases, we have the output of the previous block, all of them going into the summation. So, okay, we understand this part. Now, all of these sums are going into these yellow things, which is the sigmoid activation function. So again, this is the activation function here. Okay, so you can see there's two types of activation functions in this kind of node. So you have the tan H. I don't know if you call it the tan H or just the tan, and you have the sigmoid. So all of them, all of the summations will hit those activation functions, and then, okay, they will go to these icons, which is element-wise multiplication. Okay, so this will do some multiplication, and again goes to the tan H, this one. Here it goes to a summation, here goes to a multiplication. All of that will move to a memory from current block, so it's stored at a state. So this is the storage. This is the output of the current block, so this probably goes to the next block. So this is the output, and this one is the memory from the previous block. So we have input from previous block and the inputs and the biases coming in, and we have the memory from the previous block, and we have the output going out and the memory out of this block going out as well. So this is two outputs going out from the current block, and this is the memory from the current block. So all of this multiplication and summation, again, this is the complex part. You want to dig deep into this, feel free. But what these calculations are doing are generating values that are either eliminating something or put in the way they put it as a block for keeping the memory or giving the output of the current run, and so forth. So it's just complex calculations that will enable the architecture to operate in the way that it is designed, which is not only taking inputs and giving outputs, actually taking inputs, and like recurrent networks, taking the output of the state of previous layers or nodes. But here also, it's giving an output, and it's giving an output of the memory state of this layer or this node. This is the storage. And it's also taking as an input the memory from a previous block. So it's much more complex inputs and outputs managed for this architecture. So this is, again, more details around the input gate, controls the flow of information into the memory cell, utilizes sigmoid activation function to determine which information from the current input should be stored. So this is this part here that it's just deciding what it needs to actually store, and this goes to the storage here. So this is why it goes straight to the storage. Forget gate regulates the retention or forgetting of information from the previous time step, employs again a sigmoid activation function to decide which information is irrelevant. Okay, I will not go into these things. Fundamentally, we've evolved the RNNs into the LSTM networks. Those were equipped more with a memory and the ability to eliminate certain information, retain certain information within the architecture. So it gave it longer term memory, sort of speak, to retain its state for longer time, which helped, again, the context part of training those models. But up to this point, it wasn't, I guess, good enough that it went to the public. It wasn't good enough that it's something that you can use in models that are scaled in the way we see today. So you can see the challenge. I think even with these limitations, or even with these capabilities that the LSTMs got, it wasn't good enough in terms of context. Maybe it was good enough to do very short translations, but nothing more than that. So the conclusion, let's just read that. I think always these are helpful. In summary, recurrent neural networks and long short-term memory LSTM networks represent powerful architectures for processing sequential data. So we keep going to sequential data. This is a very important one as before we progress. While RNNs are effective in capturing short-term dependencies, LSTM networks excel in modeling long-term dependencies by incorporating sophisticated memory mechanisms. Understanding the principles underlying these architectures is essential for leveraging their capabilities in various applications, from natural language processing to time series forecasting. As research in this field continues to advance, RNNs and LSTM networks are expected to play an increasingly important role in shaping the future of AI. Okay, so again, as I mentioned in the beginning, RNNs are still an important part of the architecture. So that didn't go away. So what we're going to cover next is not like something that replaced them. I think it's the way to describe transformer architecture is one more technology that enables artificial intelligence. So these two architectures that we just covered gave us a lot. So the LSTM gave us that longer dependency retention within the network, but still it's I think the problem that remains with them is that they have this kind of sequential limitation of how the data flows through them, and that's a problem that we will look at later on and how it's solved. As of now, I think we have all the fundamentals to start looking at basic concepts that take us towards the transformer architecture and what that brought to the artificial intelligence technology. Okay, so if you're watching so far, honestly, you could be considered a saint to watch so far. And at this point, I feel ashamed to ask you to subscribe, bearing that much. I hope you're getting value if you're watching so far. So, hey, if you like it, do not forget to subscribe. I would definitely appreciate that. So now, before we go to the transformer architecture, let's talk about tokenization embedding. I think these are two concepts that at some level we must understand, not only for the case here of this video, but really for anything when it comes to understanding AI models and how they operate. So let's progress here and start with tokenization. So tokenization is the process of taking the input text and partitioning it into small, secure, manageable units called tokens. These units can be words, phrases, subwords, punctuation marks, or characters. According to OpenAI, one token is about 4 characters and 3/4 words in English. Okay, 3/4 of a word in English. This indicates that 100 tokens are approximately equal to 75 words. Tokenization is the crucial step in natural language processing. During this process, you are preparing your input text in a format that makes more sense to AI models without losing its context. Once tokenized, your AI systems can analyze and interpret human language efficiently. Let's take a look at the key steps to perform tokenization. Okay, so it's basically turning text into tokens. Tokens, as it mentions, it could be words or part of words or even punctuations. And it's just a way for the model to be able to understand the context or the text that you are entering. Basically, when it says that, turning text into numbers, this is usually the idea. So the step 1 of tokenization is something called normalization, an initial step in which you need to convert the input text to lowercase using NLP tools to ensure uniformity. So everything is lowercase. So this is new to me. So when you push something into the normalization process, you don't have caps or anything. Everything is lowercase. You can then strip out unnecessary punctuation marks and replace or remove special characters like emojis or hashtags. If you're prompting with hashtag, or if you're training maybe more accurately with emojis or these kinds of special characters, those have no value or bear no value to the model. Then you go to the splitting. You can break down your text into tokens using any of the following approaches. Word tokenization, the word tokenization method suitable for traditional language models like Ngram. It allows you to split the input text into individual words. Consider the sentence, the chatbots are beneficial. In the word tokenization approach, this sentence would be tokenized as the chatbot are, so each word in the sentence becomes its own token. Subword tokenization, so this is a different way. Modern language models like GPT 3.5, GPT 4, and BERT. And by the way, if you go to OpenAI website, they have a page dedicated to understanding how they do their tokenization. Use subword tokenization approach. This approach breaks down text into smaller units than words, which helps handle a broader range of vocabulary and complex paragraphs. Consider the sentence, generative AI assistants are beneficial. In the subword tokenization approach, the sentence can be split as, generative AI assistant and are beneficial. So it breaks the actual word into parts, so it's not per word. The character tokenization. So character tokenization is commonly used for systems like spell checkers that require fine-grained analysis. It enables you to partition the whole text into an array of single characters. Consider the sentence like, I like cats. The character-based tokenization would split it to basically each letter and even spaces, as you can see here, to its own token. Now, this is interesting. If you remember at the beginning, I told you the strawberry test, someone mentioned to me it's about the tokenization part of it and the embedding. So this is, we might have part of the answer here. I do not think that the character tokenization is the mainstream. So for example, if you go to OpenAI, they use the subword tokenization. They do not use the character tokenization. So the token, as far as the model is concerned, is not a letter. It's a part of a word. So it doesn't see letters. So step 3, so after we actually tokenize, so we've normalized, tokenized, now we're going to mapping. In this step, you must assign each token a unique identifier and add it to a predefined vocabulary. Adding special tokens. You can add following special tokens during tokenization to help the model understand the structure and context of the input data. So we'll do mapping, and I think mapping will come in later, and then we'll do the special tokens, and these will allow, again, as the tokenization to help the model basically understand the structure better. Maybe it's not really explained here, but let's take it as it is. Okay, so CLS. CLS is a classification token added at the beginning of every input sequence after the text passes through the model. The output vector corresponding to this token can be used to predict the entire input. Okay, SEP, a separator token that helps you distinguish different segments of the text within the same input. It is useful in tasks like question answering or sentence pair classification. So I think these are part of the special tokens. They just give more context for the model as it runs through the input. Okay, now embedding. So that's the really important part. Embedding is a process of representing the tokens as continuous vectors in a high dimensional space where similar tokens have similar vector representations. These vectors are also known as embeddings, help AI and machine learning models capture the semantic meaning of the tokens and their relationships in the input text. To create these embeddings, you can use machine learning algorithms such as Word2Vec or GloVe. The resulting embeddings are organized in a matrix where each row corresponds to the vector representation of a specific token from a predefined vocabulary. For instance, if a vocabulary consists of 10,000 tokens and each embedding has 300 dimensions, the embedding matrix will be 10,000 multiplied by 200 matrix, by 300 matrix, sorry. The way I understand embedding, and you can see we're talking about a huge number of dimensions, and this is something that your brain can't even imagine. But the way, if you want to think of it in our human context, so imagine you are in a VR kind of situation. So you look at things in 3D and you have all the words in the vocabulary in that space, and these are grouped. Obviously here we're talking about the tokens, so could be parts of words, and these are grouped in a way where it reflects the association of these words together. And this is why I think, like, when you do embedding, if you ever went that deep, I did it in working with Flowise. For example, OpenAI has its own embedding, so all of these tokens or words, for easier terms, are grouped where semantically they are similar. So let's say the words that have similar meaning or are correlated to each other are within similar chunks or groups within that huge space. So if you look at space, for example, you can find, let's say, door and knob. So the word door and the word knob are in one group because these are related. You can look at, another group. You can probably find cat and dog, something like that. This is how you imagine it. And each of them is represented with a matrix of numbers. It's data, basically. And that data, which is the embedding, the way I would describe it, it is the GPS, it is the coordinates of that word in that 3D space. So if I give the navigator that number, it will identify that word. But if I give it the embedding of another word, it can tell, is that word close to the original word or the initial word, or is it far away from it? If it's close, that means those are within context. Those are similar in meaning or related in some sense to each other. If they're not, well, there's not really high importance of the relationship between these two words together. So just imagine it this way. This is your navigation to the relationship between words or tokens among each other in that kind of multidimensional space, which is, here they're mentioning 300. I think the OpenAI embedding, it goes to 512 dimensions. But just the concept you want to grasp out of this, that embedding is our way of going to that multidimensional dictionary, seeing where all of these tokens are placed and how they are placed and in which groups and in terms of numbers, and are they related or unrelated to each other. So let's look at this example here. So we have the mouse ran up the clock and then the mouse ran down. So we have all of these words here. And this will come later in the transformer model. We have here the sequence of these words. So, some of them are repeated. So only here it's done once. So we have the sequence of these words from 1 to 6. And you can see again the sequence of these words depending on the input. So here you have the mouse ran up the clock. It has all the words 1 to 5. Here it has 1 to 3 and 6. All of those go to embedding layer. Output dimension is 4. And these are the numbers. So this is the embedding representation of, and this is multidimensional again, of this input here and this input here. And then you can build context just comparing all of these words and their embeddings to each other. We'll go into that later, but just remember, it's a way for us to see where those words fall into that space and how related or unrelated they are to each other. Okay, I think so. If you want to spend more time reading about this and going to the detail, you can look it up on this link here. All the links will be provided in the description. But for us, this is what we wanted to really understand. We know what's tokenization. We have an idea of embedding. Now we'll go to the really important stuff, which is the transformer architecture. And everything that we've covered so far will play a role in understanding what that did and what it changed and where we're at today because of it. So moving on, let's go to this amazing article by Dr. Ernesto Lee. So thank you, Dr. Ernesto Lee. I care of putting these resources again because of the people behind them. So Dr. Ernesto made this blog post to explain intuitively, in an easy way, the transformer architecture and the paper that basically broke that technology out of the world, which is attention is all you need. We're going to go to the paper itself later on, but I thought the first run through this is through someone trying to explain it in layman terms to someone like me, someone like you, and later on we go to the paper because it's very important. Even if you understand the idea here, I recommend to everyone to go to the original paper, Attention is All You Need, and read through it. It's an amazing paper to read. And even if you're not a technical person, you're going to grasp, I would say, at least 60 to 80% just by going through it at a different and whole new level of understanding it elsewhere. So the intuitive explanation of Attention is All You Need, the paper that revolutionized AI and created generative AI like ChatGPT. Like this title says it all. This is the technology that brought us generative AI that we know today, at least at a scale, at consumer scales, consumer level. Something like ChatGPT is just started with this technology, which came in 2017. So this is the technology that makes ChatGPT works. This is the architecture. Now we're gonna go step by step to understand this. The way I'm gonna try to explain it, I'll try to go through the architecture in my own understanding today, and then we'll go to break it down into bits and pieces to understand it further and further and further. And hopefully, by the end of it, we'll have commonly, me and you, a much better understanding of this architecture and what it means. Again, I'm not a technical person. I'm like you, trying to learn. So if you see me struggling, this is my way of making and putting things together. This is my brain, my human intelligence. Now there's a name for our intelligence called human intelligence works. And I'm training my brain to really learn artificial intelligence. So I'm running my own transformer architecture in my brain to make sure at the end of this I'll have an updated, fine-tuned model that understands AI better. So here, this is the architecture in general, and the main thing about it that you have this, what they call the encoder block. You have here the decoder block, and you have inputs and you have outputs going out, and eventually you'll have a final output, which is a probability. And the way it works is you push an input. So imagine the input as a text, similar to the examples we went through. A sentence, I ate the apple, for example, or let's make it a part of a sentence. So the apple dropped from, so what's the word after that? So imagine you put only the sentence and you end it at from. So we take that input, we go through the embedding, which we covered. So what the embedding will do, it will take all of these words, give them that kind of matrix that position them in that embedding dictionary, that 3D space where each word falls. And then we're going to do positional encoding. If you remember, just now we looked at it. So we're going to give them, the easiest term, a number that gives them the sequence. So what's the position of each word? This is word 1, 2, 3, 4. And once we have that, we push it to the encoder. Now, the encoder, what it will do, it will go through what's called a multi-head attention. And this is where the money is when it comes to the transformer architecture. This is really the brains of it. And what it does here, and what it brought to the technology that wasn't there before, it was able to give context, real context, and in a parallel manner. So this is where things are not happening sequentially. So what it does, it takes all of these inputs and positional encoding, sums them together, and what it does is push them through some kind of algorithm that will look at the embedding of each word in relation to the other words. And it will create that kind of, the easiest way I describe it, a heat map. So which words are more related to the other words. And this is from the perspective of each token that is going in. And this is why it's called multi-head attention. It all happens in parallel. So all of these kind of matrices or heat maps happen together, and you can the model will see each word and how it stacks against all the other words in terms of attention. When we say attention, what are the other words that are the highest importance to that to those other words in the input? So for example, we said the apple fell from, right? This is what we said. So is the related more to the apple or fell or from, and so forth. It will do it for each of these words through this multi-head attention calculation. And after that, it will do adding and normalizing of that data so it can process it further, and it will push it through a feed-forward network. This is your normal network here. Again, it will do an add and norm, and then the output of the encoder, which has, by this stage, all the input information with its embedding and positional encoding. So it has the meaning, it has the positions of the words, but also because it went through the multi-head attention, it has that contextual knowledge of that input, of which words matter more to which other words. So it understands the relationship between words, the easiest way to put it. And all of that goes into the decoder. Now, again, the decoder is, remember, this is part of the bigger way of how this operates. So here we want to predict the from. So this is, it says shifted to the right. So we said the apple fell from, what's after that? So that output prediction, or the expected output, goes into the same process. So let's say at the first word, nothing happens here. It's blank, I would assume. This is my understanding, because we have one input still, it didn't generate the next word. But eventually, let's say after from, it will put the. That apple fell from the, and later on tree will come, for example. So once the is generated, when it comes to running for the word after that, to put the probability of tree, the will be the input here towards the output decoder part. And it will go through the same things. It will embed that word. It will give it a positional encoding. It could be a couple of words and then, or tokens. It will go through the masked multi-head attention. So it will put the context of the output. And here it will do it again. But here it is linking it to the input. Okay. So it has previous words, the input plus previous words. It will give it like that longer context. So the apple fell from the tree. Now, maybe it will continue after that. And then it will normalize at each stage, obviously, push it through a feed forward. Then it will make it kind of a linear. Softmax is a certain special type of function that will give probability for all the possible outcomes. So for example, at this output, it will say the apple fell from the and if. So all of these are possible outputs. The softmax will give probability. Let's say the is 60%, if is 3%. So each possible output will get its own percentage. Eventually, the highest probability or the highest percentage will be the output of this. In our example, the apple fell from the tree. It will be most probably that the and tree will be the highest probable next tokens to fall after the input. This is, in the shortest sense of the form, how I understand today the transformer architecture. The thing that it did, which wasn't there before, is that masked multi-head attention, getting the context. So it understands words in a very similar way that we do. So when you hear someone saying the apple fell from the, you have the context of that statement, and because of these words, probably after that will come the, and then maybe most probably a tree. There's a context of the apple falling from somewhere to somewhere. I don't know if I complicated more for you or made it simple. I hope I made it simple. But this is, in a nutshell, the transformer architecture. If you don't really want to know more about the details of it, you can jump off the video here. But now we're going to go into really, really interesting stuff. Believe me, it's intriguing and really interesting to learn how all of these blocks work. We're going to go for it. I will not go for like deep understanding of the equation and the math behind it. I just want you to have that knowledge that will make you above 99% of people around you who understand artificial intelligence, which will enable you to do much more, if you ask me, with AI, even with ChatGPT, once you understand how this thing works. Obviously, this happened in 2017. There are developments happening around it. So I don't think today, the way they train the models, it's exactly like this. But this is definitely the DNA of it. So 90% of what they use is the transformer architecture that you're looking at. And we're going to look after that at what's happening out there that could take us to the next level of the transformer architecture. What is next there that could really even make AI models much better? Okay, so let's carry on. So this is, I gave you my understanding. Maybe you liked it, maybe not. But let's go and This is just an intro to the concept, and you can see this paper was published in 2017. It was the introduction of the transformer architecture. Okay, and you can see here, before I move forward, prior to the inception of recurrent neural networks, RNNs, and their variation of LSTM and GRU. I don't know honestly what GRU is. Write me a comment in the comment section if you know what this is. Were the go-to solutions for sequential data processing. While effective, these models had their limitation, particularly in terms of training efficiency and handling long-range dependencies with data. So it's less about the sequence here, it's more about still the dependencies. Okay, enter the concept of attention. This is why it's a brilliant title. It's like a YouTube video. If you give it a wrong title, it will not work. So they gave it a really good title. Attention is all you need. So this is why this paper focused on attention. So rather than processing data sequentially, well, I'm right. So it's more about doing things in parallel. So rather than processing data sequentially, the attention mechanism allows the model to focus on different parts of the input data, providing it with the kind of short-term memory to discern what's essential. This innovation enabled models to capture intricate patterns and relationships in data with remarkable accuracy. So, why is the paper of monumental importance? Basis of subsequent innovations. The transformer architecture forms the foundation for models like BERT, I think this is the early name of Google, GPT, and T5, which have dominated NLP tasks ranging from translation to text generation. So this is the translation, which was the thing everyone played with before, to text generation. This is the generative AI part. Elevated AI capabilities. With the power of attention, AI models can now generate more coherent and contextually relevant content. This led to enhanced chatbots, improved search engines, and more relatable language translation tools. Again, just to pause here for a second, I think at this level, you also, in your mind, you can imagine why the model hallucinates. Like the way it works, the way the transformer works of predicting the next word based on a relationship, it can easily get things wrong. So hallucination is part of this kind of idea of how it works. So the understanding of the details of how models operate, I think it will help you even navigating your interaction interfaces with AI models. Anyways, democratization of AI. The rise of pre-trained models, which owe their genesis to the transformer, means businesses and developers without vast resources can now access state-of-the-art AI capabilities. Now, doing things in parallel means, and I'm assuming here, that you need less computational power to train certain models. Obviously, with a specific number of parameters. I think the more the parameters, the more computational power you're going to need. But and this is one of the biggest problems in AI today. We know that's totally expensive. Like one of the most expensive technology to perform today is training an AI model. And that's affecting things in so many ways. So it's limiting certain societies or areas or countries to have access to the technology. So by doing these innovations, which we're not there yet, I think in the future, people are still working towards things that will require less computational power to get higher quality models. You will give access to more people to benefit from this technology, and that creates value. I know that's a different topic of AI taking jobs, yada yada. These kind of technologies, they create lots of value that maybe one of the scenarios, they remove the threat of that technology to people losing their jobs, because lots of money, lots of value will be created in the market. So you want to make it also as one aspect of looking at this technology of how do you make it accessible for more people. Again, just stop in the middle of all of this. So let's carry on. But these are some of the main importance and what this technology or the transformer architecture brought to the world of artificial intelligence. The attention mechanism explained. Imagine you're reading a lengthy novel, and every time you come across a pronoun like he or she, you instantly recall who it refers to from the previous paragraphs or chapters, instead of reading the novel linearly from start to finish and understand every sentence's context. Your brain intuitively attends to the relevant part that helps make sense of the current sentence. I think this is a better way of putting what I try to explain. But so these kind of pronouns, when we read something, we just keep relating them to the right character or the right thing, basically. So this is what the attention mechanism did for artificial intelligence. This ability to refer back or pay attention to specific parts of the text for comprehension is exactly how attention mechanism in neural networks like ChatGPT. Okay, let's take an simplified example. Let's do that. I think these, like, if it's simplified, I want to work with it. So the sentence, Dr. Lee, who loves his dog Daisy, often takes her to the park and gives her several good boys. Okay, I think this is how you pronounce it or how you say it. If you want to know who her refers to, your brain would likely attend more to the word Dr. Lee and dog Daisy to derive the context. In essence, you assign different weights to different words based on their relevance. So the weights are basically what we get out of these attention heads. Okay, so let's go to the attention mechanism. So, but you understand the stage. We want to give a mark or a grade or a weight for certain parts of the context to really understand it. So at least for the machine to understand it. And this is what takes us to this mechanism. Words in a sentence are assigned different weights. These weights determine how much focus or attention each word gets when trying to predict or comprehend another word. Connecting to ChatGPT. Okay, ChatGPT, like other transformer-based models, leverages this attention mechanism. When you pose a question, the model doesn't just look at your current message in isolation. It attends to various parts of entire conversation context, assigning weights to different parts based on relevance. This ability helps the model to generate relevant and contextually appropriate responses. So just as your brain attends to specific words in our example sentence to understand the reference to of her, ChatGPT attends to different parts of the conversation to provide a coherent reply. So it's not only looking at the input today, it's looking at the input and the context of the conversation or the thread that you're having with ChatGPT. So imagine all of that amount of data is assigned weights, and the model is able to tell what is more important to all the other words in the context for each word, so it will predict the next one. I hope I made that clear. So again, we go to the same architecture, how it looks. I went in my words of how that should be explained. I'll just go to snippets of the things Dr. Lee is highlighting here, and then we'll move to different sections of really digging deep into the sub areas of that architecture. So the first one is embedding and source sentence. So here, for example, you get the cat sat on the mat. So you input sentence, the cat sat on the mat. The model first turns these words into numerical vectors through a process called embedding. We looked at embedding, we're not going to dig deeper, but again, we turn text into vectors of numbers, which will help the model understand in the space like where that word falls. Okay, and then we have positional encoding. So this is the step we talked about, and this is the one that assigns a sequence number for each word. So the cat sat on the mat. So this is a matrix, a single layer matrix of which has the numbers of each word. So you know the sequence of the word. So you have 1, 2, 3, 4, 1 again, which is the, and then 5. Since transformers don't inherently understand the order of words, this step adds information about the position of each word in the sentence. So the word cat might get some positional information indicating it's the second word. So simply it's a number just to tell the model this is where the word falls within that context in terms of sequence, not attention. Multi-head attention or multi-headed attention. So this is the left side, because we said we have the encoder and the decoder side, left and right. So cat and sat are important and related in the sentence. So this is what happens. It runs through each of the words against all other words in a matrix based on the sum of the embeddings and the position, and you'll see why I keep using the term heat map. It will look at the numbers, and let's say the higher the number, the higher the weight, the higher the attention it should give to that word in that context. So this is the magic step where the model figures out which words in the sentence are important and relevant to each other. Here it might recognize the cat is closely related to sat, because the cat is the one doing the sitting, adding and norm. So we talked about normalization in previous networks. When we talked about the RNN, it was at that time making everything lowercase. Let's see if this is the same one here. After attention is applied, the model normalizes the data, ensuring it is in a format that is easy for the model to work with. Okay, I think this is more around numbers, nothing to do with the normalization we talked about. Full understanding of the input sentence and what words are important and what words are related. So again, this is pushing the data out of the attention, multi-head attention. So the attention data, pushing it in the network, it will get the network to understand, okay, so I need to focus on this and this and this further. These two words are linked. These two words have nothing to do with each other. It's not that important of a connection. So that's the actual network that does this understanding based on the multi-head attention. So this is just a simple neural network that does further transformations on the data. Output embedding and output sentence. So start assembling the translation and look at prior translations. So this is basically an example showing a translation of this sentence that does with the cat sitting on the mat. So the decoder starts its process by looking at any prior translations. Initially, it might just be the starting token indicating the beginning of the translation. If you remember, we had those kind of special tokens in the tokenization. So the first token, because there's no, like the first word to be translated that doesn't exist yet. So it will have to start with it. So there will be a special token that will highlight or flag to the model that this is, we're going to predict now the first word. It will not take any real output input, basically. Maybe that will confuse you, but it will not have anything coming in here other than later on the output from the encoder. So that will be the first word. After that first word is out, I think, that will be the input for the second word to be predicted. The decoder starts its process by looking at any prior translation. Initially, it might, okay, so we just mentioned that. Masked multi-head attention. So on the right side, the decoder, we have two steps of the multi-head attention. One of them is masked and one of them is unmasked. And when we say masked, if you ever dealt with images or Instagram, if you do these things, masking an image is just highlighting an area you want to keep and the area that you don't want to keep. So this is the masked multi-head. Basically, do a little bit more to just mask out certain parts and keep certain parts. This is the way I am understanding it. If you think I'm wrong, write a comment in the comment section. So what are the best words to include in the translation based on what's already been translated, but don't look ahead? So basically, this is all happening without considering what's happening later on. So not looking ahead. And based on the words being translated, focused only on the output. This is how I understand it again. This will decide, what to include and what not to include. Later on, it will get mixed with what you're getting from the input embedding and or the other output or the previous output. That will change. But for some reason, we have to do it purely without masking it purely to the output itself and to the full context. Maybe doing both will give us higher quality kind of translation or generative context of the words that the AI is predicting. The decoder pays attention to the previously translated words. This is masked to ensure the model doesn't look ahead at future words which it shouldn't know yet. Okay, so as I mentioned before, the output will be multiple options and predictions. So you don't want it to look at those future possibilities, just focusing on the previously translated words only, and later on the output will be all of these multiple options with probabilities that it will use to select the next word. I know, this can get more complex. Again, the more you dig deep into the science behind it or the math behind it, maybe more accurately, you'll understand it further. I will give you the tool to do that if you want to do that. I didn't do it myself, but I'll give you that tool. But just here, I hope you're getting the flow of what this is doing for us. We do the first masked multi-head attention, then we do the next one. Again, each of them comes with the add and norm or normalization. So the second one is using the prior translation plus the new text that was input. Remember, it is represented as a number, okay? identify the best words probabilities. Okay, so here we mix both. We take the prior translation, the new text that was the input. So we give it the first input, and then it will start predicting the input. So the first word will go to the input here. Maybe this is the part where I get confused when I look at the transformer architecture. If you have the answer, correct me. So let me read it one more time. Using the prior translation plus the new text that was input. The word here is new. It's new text that was the input. Okay, so maybe this is at the first run. Still, this is the input that we were looking at. So the cat sat on the mat. It's the same one. Remember, it is represented as numbers. Okay, identify the best words probability. Okay, so I'll take it as I understand it. I'll not complicate it. Basically, it will take the previous word, it will take the input, and it will start giving the probabilities of the next word. Once the probability of the next word comes, that word will again go here to the input, shifted right. And this is the loop here. This will keep looping, I think. So it will not go to the input. The input is standard. The loop will happen here in the decoder part. This is why sometimes they call it the encoder decoder. So I'm just presuming here. Now the decoder also pays attention to the encoder's output, trying to figure out the best words to translate next. So it might look at cat and decide the next French word should be chia, I think, or chia, I don't know. I will not try to translate here to French. Add a norm important from a tech perspective, but not so much for an intuition perspective. So, okay, we need to put numbers in a certain way for us to put the probability and the words going forward. And then again, the data is normalized. Feed for the neural network does its transformations. And then we go to the linear and softmax. Convert numbers to words. So this is the opposite of embedding. So this reverses the embedding, taking the numbers, putting them as words. And I assume this is again going to something similar to the embedding, where takes the numbers, goes to the word in that kind of 3D space we talked about, picks the words and drops it out. This is the function that does that, I assume. These steps convert the decoder's internal data back into actual words. After going through this, the model might output the word sha or shat as the translation for cat. This process continues for each word until the full sentence, I will not read it in French, is generated. Remember, this is a very simplified example. In reality, the model considers many possibility translations at once and uses complex math to choose the best words. So this is what I keep telling you about. The output will be so many words with probabilities, and the model usually selects the highest probability as the word that should come next. Okay, but this should give you a basic idea of how data flows through transformer when translating a sentence. Okay, so again, here is giving one more example. I will not go through it, you can read it, but this is the highest level or broadest level of understanding how the transformer works. Now, let's understand one concept before actually going to the multi-head attention, which I said the most important part about the transformer. And then I'm going to look with you at the paper. We will be repeating some concepts when we look at the actual paper, but I think it's very important. After that, it will be the fun part where we look at things we can have or the future, what it will bring. I keep reminding you of because this is a long video, of what's coming. So let's move to the next concept before we move to the multi-head attention concept, and then the paper of attention is all you need. Okay, so we're going to go to look at something. These are efficients or coefficients or factors that are very important to understanding how the multi-head attention works. The Q, K, and V, which is the query, key, and value. We're going to go briefly at them. I don't expect you to really understand them 100%. I don't understand them 100%, but at least this helped me grasp the idea of how important it is to the calculation that goes behind the multi-head attention. And based on that, it helped me understand the multi-head attention more. So that's the whole reason I'm covering this here. Later on, we'll go to the multi-head attention. It will be these kind of three, the query, the key, and the value will keep coming up. At least when that happens, we'll have the understanding and will not be lost in that explanation of the multi-head attention. So that's the whole idea of me covering this quickly, as quickly as I can. Okay, so let me read the introduction to this article on LinkedIn by this Chief Digital and Technology Officer at Constellar. Okay. In the realm of natural language processing, large language models, LLMs like GPT-3 and BERT, have revolutionized how machines understand and generate human language. At the heart of these models lies the concept of the QKV, and the multi-head attention are the key. It sounds cryptic to me at the very beginning, and it takes me a few weeks to figure it out. So imagine someone like that is saying, it sounds something complex for me to grasp. Took him weeks to understand it. But again, so so that's very humble to mention in such an article, very welcoming for someone like me to read. So if you don't fully grasp it, the person telling us about it didn't get it from the first time, but we just want to get the idea behind it. So the following is what has been explained in the paper. So this is the scale.product attention and multi-head attention. So these are two types of attention mechanisms, I assume, but forget about these details. Let's look at the multi-head attention. This is what we want to really focus on. You can see the way it receives the information. If you remember in the original architecture, when we looked at it, once the embedding and the positional sequence happens, we put them together and then we push them to the multi-head attention. The way it goes in through these variables. Let's call them variables for simple terms, which happen on a multi-layer. So in parallel, we have V, which is the value key, K, which is the key, and then Q, which is the query. And so let's try to understand them and see what is the multi-head attention is getting as an input for it to be able to do some calculations to give us the map of where attention should go before it pushes that to the feed-forward network. So the query represents the current item that the model is focusing on. In a sequence, the query is like asking a question about a particular element. Okay, so let's say we have the cat sat on the mat. Let's work with the previous example. When we are looking at cat is the query. This is how I understand it. So cat is the element in the sequence that we are focusing on. Key represents all items in the sequence that the model could focus on. The keys are what the query is compared against to determine how much attention should be paid to them. So the key, I would say, is the other words. So if the query is cat, the key would be the sat on the mat. So without the cat. So it's all the other values that the query is measured against to see where attention is going. The value, each key is associated with a value. Once the model determines which keys are important based on the query, the corresponding values are used to construct the output. So each key is associated with a value. So I think this is the value. It could be an input, but at the same time, it is the main output out of the multi-head attention, I think. So let's read on. But this is the value that we have now. We know what's the key. We know what's the query. So the query is the word. The key is everything else, the context around that word. The value is what gives that weight. Let's use the original term of each of the key parts of where attention should go more or less when it compares to the query, which is cat. So let's read this part. Maybe this explains it a little bit more. A simple sentence like Tom is going to fish at the riverbank is easy for us to understand. To let computers understand it, we need to encode every word into numbers, which is called word embedding. That's we understand. Assuming in a simple 6-dimensional space, the word river can be represented as a word embedding of, he gives it just numbers just to show an example of the embedding of the word river. Those words with a higher similarity will be close to each other. For example, group 1, river, fish, and fishman Group 2, hospital, post office, and restaurant. It becomes interesting when we try to figure out where to put the word bank. It is a polysemy that can be interpreted differently based on the context of the sentence in which it is. Okay, so again, this is just about the embedding still, and we talked about it, that 3D space and imagining how these groups of embeddings are put together. So different tokens are more relatable to each other. So he's just explaining it in simpler terms the same way. But he brings an interesting point. So bank, the word bank, it could be here closer to this group or closer to this group. So river bank. So how does it differentiate, or the bank itself? So how does it differentiate where this should be associated with? I think this is his question here. When we read it, we know a bank cannot be the place where you draw money. Why? Well, the presence of the words river and fish contribute more to our understanding of the context compared to the rest. Therefore, they should have high attention scores and be closer to bank. Okay, so let's go back to the important part where we're going through this article, which is the query key and value. How does a computer determine that it should pay more attention to river and fish and not others? This is where query and key comes in. They are two linear transformations that help answer the question. Within this sentence, what are the similarity scores among the words? Firstly, okay, so here we have all these linear matrices. So we have each of them as a linear matrix, and you can see these are a bunch of numbers. Some of them, when you do a certain calculation on it, will be closer or farther away from each other. So I think river is the query. So the river is the query we're looking at. The key is everything else. So the multi-dimensioned, basically, when you put them together, matrix of the other words. So this is just visual depicting the key and the query here. So we have the bank and we have the river similarity. Okay, so this is just showing you how all of these come together. You can see the value, which is kind of putting together the query and the key. So we have the width of the matrix, the dimensions based on the query, I assume here. Here you have the rest of the keys. I think this is like inverted. The matrix is inverted here. So all of this is mathematical operations that happen to the embedding and positional data that comes in to make sense of it. The easiest way to put it. And then you get the value. This is the value that tells us, okay, this token is more important to this token, and this token is less important to these tokens. The output goes through the steps: match, mule, scale, mask, and softmax. All of these are operations, mathematical operations that are needed to prep the data to go into the multi-head attention, and even later on to be pushed into the feed-forward network, and even to be pushed as words that we get from the model. Now, the previous article, if you remember, Dr. Lee didn't want to go through that because he wanted to keep what's important to understand the context of the transformer. Here, it's going a little bit through that. I want us just to grasp the concept of how the query key and value work. So just understand that math, mule, scale, mask, and softmax. So we looked at mask like the masked multi-head attention and the unmasked one. So just understand that these are mathematical operations that happen to manipulate the data. This is the easiest way to put it. We are manipulating the data to be able to get really the output that we want. And there's lots of computing behind it and lots of genius kind of mathematics people created to really get us to that. So we're not trying to fully understand that today. So let's carry on. We then have the final output, a weighed sum of these values, where the weights are determined by how well each key matches the query. So we're just matching those keys to the queries. We're giving it values, the V, and that's it. We're good to go and use that information. So the new embedding compared to the original one captures more contextual relationships. I think this is what happens in the multi-head. This is this is a single head of the multi-head attention. So it's all functions that the query and the key goes through. Eventually, the value is added, which we'll have to really grasp later on. Is the value just the input embedding, or it's an outcome of the whole thing? So, but what I understand, at least from what is being said and the graphic here, is that the input is one, which is the sequence and the input embedding. We take it through certain functions that, based on the query and the key, will tell us what's attention should be given to which keys compared to the query. Eventually, that output will be different from the input embedding, goes in with the value, which go into that math mule here and really give a matrix that contains the information of attention for the key and the queries. And this will happen for each query within all the possibilities of the keys in parallel in the multi-layers or multi-heads of that attention calculation or manipulation of our data. Hopefully that makes sense. So this is just a look at how maybe the possibilities are looking when you match each query with the keys, and it generates numbers. The higher the number, the more attention is given to that key. I think this is interesting. So this part is just saying that is one set linear projection representing so-called attention head. Okay. Well, okay. Yeah. So here it mentions that this is also applicable to images somehow. So you can use it for images to understand the objects in this image. If you remember, we covered the convolutional networks, and I told you transformers didn't only revolutionize the neural networks, the general ones. It also affected the convolutional neural networks, which has to do with images. Anyways, so we understand the concept of Q, K, and V. Those are the embedding. Now, the query is the part of the embedding that handles the word that we are looking at. The key is the input embedding that handles everything else that is in relation to the query. And the value is, in theory, the weight that is given that could give us the understanding of attention for these words. They go through certain functions. At the end, we have a big matrix, multidimensional matrix, complex one, that contains all of these information. It has the sequence. It has the attention, the relationships between the words. It has the queries and the keys and the values. All of it is put in one huge matrix that we later on, if you remember, normalize and push to the feed-forward network. So that's just a concept that you need to grasp. Now we can actually go and look just at the transformer when it comes to the multi-head attention and go a deep dive on that, and then we will go to the paper. Want to give more time for the part of the transformer architecture that really gave it its superpowers and the importance that it got and everything it brought to us from 2017 so far. So this is a paper by Ketan Doshi around the multi-head attention particularly. So let's scroll down. Okay, so how attention is used in the transformer. Attention is used in the transformer in three places: self-attention in the encoder. The input sequence pays attention to itself. So this is the self-attention. Again, this is the encoder. This is the decoder, if you remember. And you can see that now, I think all of you should, if you paid attention, you should understand what is happening: position, encoding, embedding, target. This is, input and target. So this is the target word, so I was correct. So you understand how these things work. So you now have, you're more savvy when you look at the architecture. You get it. We want to just dig deeper into these parts of attention: the encoder, decoder attention, self-attention. We want to dig deeper in that and really try to understand it, because this is where the money is when it comes to these to this architecture. So the first one is self-attention in the encoder. The input sequence pays attention to itself. Self-attention in the decoder, the target sequence pays attention to itself. And encoder-decoder attention in the decoder, the target sequence pays attention to the input sequence. Okay, this might have been very broad or not articulated in detail, but this is the beginning of this article. But for us, we understand is here, this is the self-attention for the input. I'm just simplifying it. Here, this is the self-attention of the expected output or the projected output. This is the encoder-decoder attention, which is the attention for the expected output plus what we get from the input. And then this goes to the output probabilities in layman terms. Okay, let's go to the more details within those self-attention mechanisms. The input sequence is fed to the input embeddings and position encoding, which produces an encoded representations for each word in the input sequence that captures the meaning and position of each word. Okay, so this we get, which is the embedding again and the sequence, position sequence. Now let's carry on. This is fed to all three parameters, query, key, and value, in the self-attention in the first encoder, which then also produces an encoded representation of each word in the input sequence that now incorporates the attention scores for each word as well. So now see, it's easier to understand because we already looked at the query, key, and value. So we take the embedding and the positional encoding. There's some manipulation that happened, and out of that manipulation, we take the query, which is the word we're looking at, we take the keys, which is other words, and the values. We push them in a way that will give us, let's say, a body of information or a matrix that contains the attention relationships of the input keys that we have within our tokens. Okay, so we have the input or the encoder attention figured out in a data block. Let's simplify the term to this. Okay, so as this passes through the encoders in the stack, each self-attention module is also adds its own attention scores into each word's representation. Okay, so this is just one graphic to look at. So we have input embedding and position encoding. It goes, so you have a matrix here. Okay, there's a sequence and there's an embedding. Obviously, this looks as a single layer. I don't think so. This will be multi-layered even at this stage here. And then some manipulations that we've seen before happen that breaks it to a value, key, and query. These are, again, functional manipulation. I want to remind you, things that we play with the matrix to get parts of the matrix, modified matrices with the same size or different size, that we need to have the value, key, and query, which each of them, as we know now, gives different piece of information. All go to the multi-head self-attention, which is again a different level of functions that run through these different matrices. And then we get the encoder output. We go and feed it back to the second layer here. But before we do that, remember there's normalization here, because the way the output comes out of the encoder has to be normalized before it goes to the encoder decoder attention in the decoder. But here it's clear because here they're showing the normalization. So here the same happened, output embedding and position encoding. This happened for the next sequence word. This is the matrix that we have. Then we manipulate it again for value, key, and query. It goes to the self-attention manipulations of its own, so different type of functions. It will give us all of the information we have so far in this one big matrix that we normalize. And that matrix that we normalized goes as the query for the encoder decoder attention. This is like the interesting part here. What we get here is from the input is the value and key. So the only thing we're getting from the input is the attention of the query and its relationship to all the other keys, while the query becomes the expected next output word in the decoder. Okay, so decoder self-attention, now I explained it, let's just read it quickly. Coming to the decoder stack, the target sequence is fed to the output, embedding and position encoding, which produces an encoded representation of each word in the target sequence that captures the meaning and position of each word. This is fed to all three parameters, query, key, and value, in self-attention in the first decoder, which then also produces an encoded representation of each word in the target sequence, which now incorporates the attention scores for each word as well. So this is the same what happened in the encoder, we understand it. Now we'll go to the encoder decoder attention, which is the interesting one. Along with that, the output of the final encoder in the stack is passed to the value and key parameters in the encoder decoder attention. The encoder decoder attention is therefore getting the representation of both the target sequence from the decoder self-attention and a representation of the input sequence from the encoder stack. Therefore, produces a representation with the attention score for each target sequence word that captures the influence of the attention scores from the input sequence as well. As this passes through the decoders in the stack, each self-attention and each encoder decoder attention also add their own attention scores into each word's representation. So that's a mouthful. The way I will simplify it to you. So, and this is why it's important to understand the query key and value. So when we do the encoder, we break down the inputs into the key, value, and query. We look at the query versus all the other keys. We assign values to them. We get the output as a matrix. Now, the decoder part, the output part, as we are producing the next token or next word and the probabilities, we are doing that, number one, in relation to the words and that were generated and are being generated. Also, we're keeping that as a query as a whole. In the second layer, we take it only as a query, the output of the first decoder self-attention phase on the right. We take it as a query to the second encoder decoder. So we look at the word that is being predicted in context as well. So we have the information of the attention with the input itself. So it's linking everything to each other. So not only we do it once, looking at the words where the input is, how the input keys are related to each other, we actually do it to the output also in relation to itself and in relation to the input. So if you want to think about it, all the words in the input and the output going through the transformer are mapped in terms of attention of these words to each other. All of them. Input, the previous words in the output, and the possible words in the output coming out. So this is how we decide the next word. So the more we generate output in relation to a certain query, we are looking at the input, the previous outputs that were generated at high probability, and the next word is decided at the attention based on all of these keys together, put together in that complete context. So we're not only looking at the input, we're not looking only at the output, we're actually looking at the whole, the model is looking at the whole thing when it's predicting the next word. This is the power that made generative AI be able to give us words. It still hallucinates, we know that, but for many ways, it gives us the next word, which is highly probable and expected term or word within the model that is generating that makes sense even to us as humans, because it's looking at complete context. Now, we're doing it with a very small examples like the cat sat on the mat. Imagine that at paragraphs. This is what you do with ChatGPT and Claude today. So the whole context is part of it. And I assume today, from what we've read so far, even the thread, the whole context of the chat, the open chat, is part of that context. And now in OpenAI, they actually gave it memory abilities. So everything that you interact with when it comes to ChatGPT potentially is also part of that attention calculation in the transformer. So this is like the whole idea that was generated in the transformer architecture gave that open door for doing all of these manipulations where you can actually generate real context in the data that you provide the model, and you gave the model the ability to see that context that in the past it wasn't able to see at in parallel, which helped the computing, and where in the past as well it couldn't see it at longer context or longer sequences of dependencies. Okay, before we move on to the paper, let's just look at this, the multi-attention heads. In the transformer, the attention module repeats its computations multiple times in parallel. So this is why they call it multi-head attention, so or multiple attention heads, because it does it multiple times in parallel. Each of these is called attention head. The attention module splits its query, key, and value parameters n ways and passes each split independently through a separate head. All of these similar attention calculations are then combined together to produce a final attention score. Now, the way I understand, even the splitting of the query, keys, and the values is done in different way. I'm assuming, if my understanding is correct, correct me if you know more in the comment section, is that it will do it for each query. So each word in that context and the other keys. So if we're looking at cat, we look at the other keys. If we're looking at mat, we're looking at cat as a key, not a query, and so forth. So we have that multi-head calculation happening at all. Then all of it is merged, and we have a matrix eventually that encompasses all of that attention relationships within it. Okay, attention hyperparameters, again, the embedding size. So here, if you want to carry on with this part on your own, this is interesting. I did a quick read for this. It just, again, explains similarly to what we did already. It shows you the way these matrices are being manipulated, changed, modified, masked, whatever you call it, for us to get the end result that we get. So splitting of these matrices, masking these matrices, reshaping them. You can see all of it here. Again, for me, I want to understand that this is happening. You can see swap and reshape. I want to understand that this is happening to get to the result. Maybe at a later stage, I will go more into the actual calculation that happens for these matrices to get what we get. If you're interested, I'm going to give you this link as well as everything else. You can see masking here. And yeah, so just understand that this is part of the manipulation. Now, I think even if you stop here, you understand the transformer architecture for the most part. I want to spend a little while on the paper itself. I will not go through everything because at this stage, I think we covered it. And then I want to go to the future and the cherry on the top, me giving you certain tools that took me some time to find that are amazing for understanding this at a whole new level, even more than what you can get out of this video. So let's go to the actual paper. So this is the paper. Again, I'll not go over the names of the great people that gave us the transformer architecture. The name, which I said it's an awesome name. So whoever is doing this actually could be really good in doing YouTube videos. Attention is all you need. Okay, I will read the abstract quickly. The dominant sequence transduction models are based on complex recurrent or convolutional networks, neural networks, that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. So basically, they're removing the whole concept of recurrence and convolutions, and they're solving so many of the problems that we covered in those kind of attention heads that we talked about in the architecture, where it encompasses all of the information the model needs really to be able to predict the next word. Our model achieves, again, these you'll see all of these kind of BLEUs. These are what I read about online. These are kind of metrics related to translation accuracy. So don't worry about it. So because the example or the testing, they did the training for preparing this paper, they did it for a translation kind of job. So our model achieves 28.4 BLEUs on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLEU on the WMT, yada yada. So just saying how well the job did or was done when using or when deploying the transformer architecture. So again, I'll just go to certain things that I think are interesting to read. Everything else, you can read it for yourself. It is definitely something everyone should read. But we already, I think, covered the important parts of the transformer architecture. So let me go to the model architecture. Most competitive neural sequence transduction models have the encoder-decoder structure. Here, the encoder maps an input sequence of symbol representing X, so these are the inputs, to a sequence of continuous representation Z. Given Z, the decoder then generates the output sequence of symbols, so these are the Ys, the output, one element at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. So as we already explained, it takes the input and the output that it predicted as an input as it predicts the next word and the one after and the one after. And this goes through the encoder-decoder stack. So this is the original, you can see even it looks cleaner, the original architecture that was created by this team. Okay, so attention, I just want to read again. Lots of repetition here, I know, but it will just help. So I want to read you attention in their words. An attention function can be described as mapping a query and a set of key value pairs to an output where the query keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query, with the corresponding key. We already discussed that, keys and queries, relation and values. Scale.product attention. Okay, so this is what, again, here what we discussed before. But again, these are the functions, just to make it crystal clear if I didn't yet do that. These are the functions that you have here. So in the multi-head attention, in each head, in each layer, you go through each of these manipulations or modifications that we talked about. You can look any of them up and see the calculation behind them. So just to make this crystal clear. So we covered that. We have the Q, K, and V. We get everything that we concate later on, basically put together, group, make it linear, so it goes to the feed-forward. Everything has to go linear to go to the feed-forward neural network, okay? You can get the softmax and the equations related to it here, and they talk about the multi-head attention that we already covered. Again, the equations are all mentioned here. I think it gets more complex than this. They just put it in a paper for peer evaluation, I would assume. So people who are evaluating this paper probably know these concepts. They're just giving them the high level modification of the architecture that they've done, like what's they're bringing as a change, all the other sub calculations that you need to figure out for you to be able to just look at these kind of seemingly simple calculations. You must already have knowledge of. So don't think it's as simple. I don't think it's as simple. And I'll show you something that will help in that sense later on. Applications of attention in our model. Again, how the attention is used. Positive-wise feed-forward network. Embedding and softmax. Again, how you embed something and how you turn it back to a word. Positional encoding. Again, some details around how that works. It's not simply 1, 2, and 3. There's some more details around that. So in all the articles we looked through, it was only simple sequential numbering, which is, as you might have expected, is not the way to do it, or probably not the way to do it. And then why self-attention? This is an important part I want to read. In the section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used out for mapping variable length sequence of symbol representations. Again, the inputs to another sequence of equal length, which is the Z's here, with this is actually the function that compounds all of the summations of the inputs and the weights together, such as a hidden layer in a typical sequence transduction encoder or decoder, motivating our use of self-attention. We consider 3 desiderata. I think this is how it's pronounced. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized, so done in parallel, as measured by the minimum number of sequential operations required. The third is the path length between long-range dependencies in the network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the path forward and the backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and the output sequence, the easier it is to learn long-range dependencies. Hence, we also compare the maximum path length between any 2 inputs and output positions in network composed of the different layer types. So basically, what they're saying here, as I understand it, is one of the amazing things about the transformer architecture is doing this multi-attention heads in parallel will reduce the length between input and the output, and in simple terms, it will allow it to contain or maintain more context or more dependencies within that range compared to doing things in sequence. And this was one of the problems that we had when it came to the recurrent neural networks, if you remember, and the convolutional ones, which they refer to in the beginning of this paper. As noted in table 1, the self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires ON, okay, this is the sequential operation. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length N is smaller than representation dimension. Okay, so this is again some of the equation context of this paper, which is most often the case with sentence representations used by state-of-the-art models in machine translations, such as word piece and byte pair representations to improve computational performance for tasks involving very long sequences. Self-attention could be restricted to considering only a neighborhood of size in the input sequence centered around the respective output position. This would increase and maximize. Okay, we plan to investigate this approach further. So at that time when they did it, it wasn't figuring out everything they need to figure out. But I think here what they're talking about is how this architecture would support reducing the computational requirements, I assume. A single convolutional layer with a kernel. So if you remember when you looked at convolutional layers, there's convolutions and kernels. And again, this is why I touched on it in the beginning. While I didn't dig deep on it, the transformer was a big shift and big change for even the convolutional neural networks. So here they're just saying a single convolutional layer with a kernel width of so-and-so does not connect all pairs of inputs and outputs positions. Doing so requires a stack of convolutional layers in the case of contiguous kernels, or in the case of dilated convolutions. Increasing the length of the longest path between the two positions. Again, this is the path sequential aspect of the neural network, but for convolutional networks. Convolutional layers are generally more expensive than recurrent layers by a factor of k. Separable convolutions, however, decrease the complexity of considerably. Even with k equal n, however, the complexity of a separable convolution is equal to the combination of self-attention layer and the pointwise feed-forward layer, the approach we take in our model. Okay, long story short, even for the convolutional network, this optimizes the computing requirement for training these models. Here they talk about the training with some equations, numbers, and results, and then they conclude their paper. Here you can read it. Even you have a link to the original GitHub repository for the architecture if you want to go there. I will have the link for this paper as well in the description if you want to go and see the actual code for this architecture as the same team that created the paper put forward. The link is here, so it's an interesting to look at. Now I'll spend short amount of time to give you an idea of what's coming in the future when it comes to future architecture to expect, and I'll give you at the end the amazing things that will help you understand this at a deep level if you want to do that. Now here, this is one more article that I'll give you the link. I'll not go through it. It will focus on what did the transformer architecture change, where it was solving a problem, what it's the downside, like what are the gaps in the transformer architecture, and maybe what's the future to solve that. It's a very interesting one. Just go read it. It's interesting. I went through it quickly. Now, there is the main architecture people are talking about today on the internet that could be the future and the next stage of evolution after transformer architecture is something called the Mamba large language model architecture. And this is what they say, this is the new paradigm in machine learning. This is the new thing. It's not fully cooked. I think it's, as an architecture, it's there. I'll give you the link to that architecture. It's not stable yet. It has its problem, but it's deploying a technology that we'll touch on quickly that has high potential of taking, this to the next level when it comes to transformer architecture today, and going to the next level of contextual understanding of the inputs that we have and the outputs within the large language model training. But I think the main aspect of the Mamba is the reduction of computational needs for training these models, which will become something very important, if not the most important things, because at some point, training these models might become so expensive that it will be also so expensive to fail at these trainings, because you expect that companies, when they train the models, they're taking a chance on the design. It might not work, it might work. If it's super expensive, not to mention that it will limit the accessibility to certain demographics, but also it will deter corporates and organizations from actually training more and more models, and it will slow down the technology. We don't want that. So there will be a big focus on reducing the computational requirement for these models. So let's go to the important part of the Mamba to understand what the hell is the Mamba, and then we'll move forward to the interesting stuff of the tools and the visuals that we can play with. Okay, so this is as recent as 2023. So in late 2023, researchers from Carnegie Mellon and Princeton University published a research paper that revealed a new architecture for large language models called Mamba. Mamba is a new state space model architecture. So this is the technology I am talking about. State space model architecture. You can read about it more. Concerned with sequence modeling, it was developed to address some limitations of transformer models, especially in processing long sequences, and has been showing promising performance. Okay, what is the Mamba? Mamba is a new large language model architecture that integrates the structured state space sequence S4 model to manage lengthy data sequences. And I think this is much more in terms of sequence to what we have with the transformer, even today in 2024. So combining the best features of the recurrent, convolutional, and continuous time models. So you see those are still alive, the recurrent and the convolutionals. S4 can effectively and efficiently simulate long-term dependencies. This allows it to handle irregularity, sample data, have unbounded context, and maintain computational efficiency throughout the training and testing. So three main things. It will allow it to handle irregularity in the sample data. It will have unbounded context. That's a big claim to make. And it will maintain computational efficiency throughout training and testing. So each of them is a breakthrough by itself. Now, the architecture is promising all three. Expanding above the S3 paradigm, Mamba brings about several noteworthy improvements, especially in handling time-variant operations. Its architecture revolves around special selection mechanisms that modifies the structured state space model parameters according to the input. As a result, Mamba may successfully filter out less important data by focusing only on crucial information within sequence. According to Wikipedia, the model translations from a time invariant to a time varying framework, which impacts both the computation and efficiency of the system. So it has, I think, this state space model is a different mechanism for capturing the context and the attention information within the model. So the main features, again, the selective state spaces. This is something to read about, particularly spend time on it if you're interested. All of it is something that is happening through the research. Remember, I think at a point of time, we viewed the transformer in the same way. People just improved it with time. It became mainstream thing. The same goes here. So what we are looking at here could be in the future the state-of-the-art technology when it comes to artificial intelligence that everyone talks about, and people will refer to 2023 when this paper came out from Princeton and Carnegie, whatever. The amazing people behind this kind of research in AI. Simplified architecture, so it's simple in architecture. Hardware-aware parallelism. So again, doing things in parallel will reduce the hardware requirement, will make the barrier lower for computing and doing more with training these models. So again, the link will be there. You can go through the architecture, but the most thing to understand, it's definitely an improvement over the transformer. In theory, they're saying it allows for unbounded context and it will reduce the computational power and it will handle irregularities in data. So that's, I think, a big thing. I don't know what goes behind the statement. I'm sure it's more complex than just the statement itself. So read through it. It's very impressive and interesting. I did some reading there. Now, one interesting part that I'll give you another link where you can actually read it in a similar intuitive manner. Some kind of simpler conversation around what it means, how it's done. But also the architecture for the Mamba is on GitHub. So okay, let's just jump to the interesting part before we close this video. If you're watching so far, I don't know, you should write your name in the comment. If you really watched this far, I'm not joking. If you actually watched this far, you should be a super fan, a super friend maybe. Write a comment in the comment section. Definitely that tells a lot about your interest in artificial intelligence. It will encourage me, even if there's one person who writes a comment with their name that they watched this video end to end. One person for me made all of the effort of creating this video worthwhile. I helped someone. This is the whole concept behind this channel, helping people. So if I helped one person, perfectly fine. I spend hours working on this. If you're here, you're that one person. Don't forget to subscribe to my channel and write a comment, engage with me. So I'm going to give you 3 things that you can use to build things on your own or play with these architectures on your own, and one that you can use it to visualize everything we talked about and even show it to others. So the first one is this GitHub repository created by this amazing person I found on X. This is his handle here. He has his Tom is Tom Ye. So he created this repository where you can download the code base here. And what you interact with is actually an Excel file. So you don't need to be a coder at all. Just go to this repository, which I'll have in the description, download the code. So you can click at the code here and download the zip, unzip the folder, and you can look, for example, at the transformer. Open it. You will see step-by-step calculation from the input until the output, going through the encoder, self-attention decoder, and then the unmasked self-attention of the encoder decoder, and then the flattening and everything we talked about until the output in Excel. You can see the equations, you can see how it works. It's an amazing thing if you want to dig really, really deep using a tool that is intuitive for most of us as Excel. Please download it, and if you go to his account here, you'll find all his social media handles. Follow him. Again, I'm sure someone like him, not only he helped people like us who know or want to learn more around AI, but also he might put forward things in the future that might interest you. You can see I'm already starting his repository. The second one is basically the Mamba repository. So we talked about the Mamba architecture, which has its issues, but still it's on the forefront of things. This is the repository. If this is your thing, if you know how to handle these type of code, maybe with AI, I never tried to do this myself to train a model. Usually doing like serious training of this will need really super computational availability or a budget that you can do to do it on the cloud. So if this is your thing, the actual architecture is an open source on GitHub for everyone to play with it by the people who created it, again under this account here. So I'll give you the link. Let me start this one as well, just in case. So go and check that out if this is your thing. The third one is an amazing GitHub repository that someone created. That's the person here. Let me start this one as well. I already followed this account after I've seen the work that they've done. This is basically an application. Once you run it, it will create an amazing visual that will showcase to you how the whole cycle of the transformer works, and really it will help you understand everything we talked about visually. I think it's very important to go through the whole context, to read these articles, to have a robust understanding. The visual will be a cherry on the top, but even if you want to skip and just look at the visuals, that's your thing. That's also nice. The great thing, this same repository, if you don't want to download it or fork it and run your own code, I'll put the link. They are already hosting it on a website, which is this one. And here you can actually see step by step the transformer working. So it's called the Transformer Explained, and this is based off the deployment of the GitHub code. And you can see here I already played with it a lot, and you can see what I've done here as the input. In the word strawberry, the count of R is, and I'm getting 1. Now the interesting thing here, when you play with the temperature, the probability, if you see here on the right, you have all the output probabilities that we talked about in the transformer architecture is here. So as you play with the temperature, and this is why you can tell the temperature is a very important variable or hyperparameter in AI models. It will change what the next word is. Okay, so it's now the. So at I think this is 1. At 1, it becomes, the next word is becomes the, and then 0. So you can crank this up, 16, 10. I think one of them should be 3 at at some point, at certain modifications. You can even change the input and see when you will get the actual correct number. But now that we understand how embedding works, and again, when you play with this, you can actually click on it, see some details. So you can see this is the token embedding happening here. It's added to the positional encoding that we talked about. All of that is pushed through the, let's go to the actual multi-head self-attention. So what do you see here? These are the Q, K, and V. So all of them are done in different heads in different ways. And you can see here in real time when you run it. So let me just hit generate here. So you can see how it runs, and you can see in real time if you hover, I think, over. So you can see here even this is the heat map, what I kept referring to as the heat map. Is shown here. If you click on this, at one point, I think you can see how the keys and yeah, you have to hover carefully at one area. Yeah, so now I got it to appear. So here you can see the QKV calculations, and you can see it's happening for each of the queries against all other keys, and it's doing it and it's generating this big matrix. This is the QV, KV weights all in one big matrix, and then it's adding the bias, and then it's getting all of these again different outputs for the multi-head attention that we have here in the visual, based on this is the visual depiction of what you've seen here, and you can see like how it links. So you get the query in, you get the key in, you get the value, if you remember, directly to the output. All of that goes out of the multi-head self-attention box. Here where we do the normalization, and then you have the feed-forward network. This is the feed-forward network. And then we start getting the 11 more identical transformer blocks. Okay, these are the outputs and all the probable next word. So all the probabilities for the next token or output. And usually you get here what is the most probable next output. And you can, by the way, you can just highlight this, write something else. So my name is, let's say, see what this generates. You hit generate, it will run the whole network for you, and it will give you the next probable word. Again, this is based on 0.6 temperature. So it is predicting that my name is A. So which doesn't make sense. Let's push it to 0.8. It's giving something else. So you can put, for example, I put my name is Samer, run again and see what I get as next. So the whole concept of this amazing work by this group is to predict the next word and through the transformer architecture, but also view it in real time, how it works. Look at the calculations of the QKV, how it happens. Look at what goes into the normalization. Look how that's pushed after flattening into feed-forward network, and how you have all the probabilities as outputs. So I know it has been a really long one. I hope you got more value than you suffered of me talking and reading all the time and just explaining things over and over and over again. It took me really a similar effort to do these things, to go through these things, to really grasp them well. I'm not an expert yet, but I'm on that way where I think I have a much better understanding than the average person when it comes to not only how neural networks and AI works, but also going at a deeper level of really understanding how the transformer architecture works, what's coming in the future, how the calculation in theory happen, and why it works as it works, and basically answering or understanding or learning from one of the people of this community who told me, well, that's why it doesn't get the strawberry test. Now I get it. So thank you for triggering this whole boring movie. And I know it might not get more than 10 views. I'm good with that. If I get one person to comment in the comment section, if you enjoyed it, even if you got like from one of the chapters, like through one of the minutes in this long video, I assume value, please consider subscribing to my channel. And with this, I'll keep it short. Thank you and goodbye.
Subscribe to Daddy's channel. Give me the mic.